Good afternoon, everyone. My name is Eunji from Seoul National University. Today, I'll introduce JANUS, a system that unifies two distinct paradigms in deep learning frameworks to achieve the performance and the programmability at the same time. This is a joint work with Sungwoo, Gyeong-In, Seong, Dong-Jin, and my advisor, Professor Byung-Gon Chun. Let me start with briefly explaining about two paradigms in current deep learning frameworks. As a deep neural network is composed of thousands, millions of mathematical operations, deep learning frameworks helps users to easily represent the computation and also execute it efficiently. As neural networks are becoming larger, deeper, and more complex recently, a lot of deep learning frameworks have been created. These frameworks can be classified into two categories, symbolic and imperative, based on how they represent and execute the computation. In symbolic deep learning frameworks, users must build symbolic data flow graphs that represent the mathematical expressions they want to evaluate, and then the graph is executed later to retrieve the result at once. Here, when a user invokes a multiplication API of a symbolic deep learning framework, a graph operation that represents the multiplication is appended to the graph, and the actual multiplication is executed later when running the graph. On the other hand, in imperative deep learning frameworks, the computation is directly executed. Therefore, when a user executes a multiplication, the product is directly evaluated. These two approaches have clear advantages and also limitations. In terms of performance, executing symbolic graphs can be more efficient than imperative execution, since the framework can see the entire computation before actually running it. So we can apply compile optimizations, execute multiple operations in parallel, and also deploy the graph to GPU, cluster, or mobile environments more efficiently. On the other hand, as imperative deep learning frameworks can only see a single operation at a time, such optimization is much harder. Next, in terms of programmability, it is much difficult to write programs or debug them in symbolic deep learning frameworks due to their decoupled view of graph generation and execution. It is much easier to write programs with imperative programming model. So, due to such advantages and also limitations, people want to take the only advantages from each side. This is the motivation of our system, unifying two paradigms to make deep learning easier and faster. JANUS tries to combine the advantages of each approach by transparently converting imperative programs into symbolic graphs. To show some preview of the evaluation results, JANUS runs 11 unmodified imperative deep learning programs in 5 major neural network categories, including convolutional, recurrent, and recursive neural networks, generative adversarial networks, and deep reinforcement learning models. And JANUS achieves up to 47.6 times speedup compared to imperative execution, which is comparable to symbolic deep learning frameworks within only up to 4% performance differences. For the rest of this talk, I'd like to explain how we could achieve such an impressive result. First, I will show you what challenges exist when converting imperative programs into symbolic graphs. Then show how JANUS solves the problem. Finally, I'll show you the evaluations. As I said before, JANUS converts imperative programs into symbolic graphs. Here, I'd like to make it clear that we are considering Python as the language of imperative APIs because it is the de facto standard language for machine learning and deep learning frameworks. However, converting a Python program into a symbolic deep learning graph is not trivial because Python programs have dynamic characteristics which are hard to be represented with deep learning graph operations, since the deep learning graphs are usually considered to be static. To be more specific, in Python, various program characteristics, including control flow decisions or types of each expression, are determined while executing the program. Moreover, such characteristics can change over multiple invocations of the same program. On the other hand, it is commonly required to provide such characteristics for building deep learning graphs. So as you can see, we have a problem here. That is, the characteristics are required for building symbolic graphs, but the imperative program have no information about such characteristics. Let me show you an example of a real-world model named recurrent neural network. With this example, I'll show you 3 representative dynamic features of Python, including dynamic control flow, dynamic types, and impure functions, which are hard to be converted into static graph elements. Also, I'd like to explain how the discrepancy between dynamic Python programs and static deep learning graphs can affect the correctness and the performance of graph execution. An RNN model takes sequences, say sentences in natural language, and process each item in sequence, for example, each word in a sentence, in a recurrent manner. We can think of 2 possible versions of the converted graph. The first version contains control flow operations as the graph elements. Therefore, it requires no information about runtime decisions on the control flow. If we generate the graph in this way, all semantics of the original Python program can be preserved. So we can say that the converted graph is always correct. However, since the dynamic control flow operations disable many potential optimizations, the converted graph is not so fast compared to the second version. If you remind the previous workload, the length of 2 sentences was both 3. So if we can exploit this fact, the graph can be much simpler by unrolling the loop 3 times in the graph. In fact, we have measured that the unrolling control flow can achieve more than 2 times the performance difference improvements in variable neural networks. However, there exists the possibility that the same program can be invoked with different contexts, say when we're training the same model with the same code, but with a different set of input sentences with variable length. In this case, using the generated graph can produce incorrect results, since the graph generated based on the different contexts. In addition, the program itself does not include any information about the control flow decisions. A similar problem exists with the dynamic types of the program. This RNN example includes expressions with dynamic types. For example, the input parameter sequence does not have any explicit information about its data type or array dimension specified in the program. It can be only determined by the input data, which will be fed at program runtime. And moreover, it is possible that the input data does not have any certain one certain type or shape. In other words, the input can have dynamic types. Given this dynamic type of the Python expression, if we'd like to generate a correct graph, as the type of its expression is not determined before executing the program, we have to generate numerous graphs with all possible combination of every data types, which is very inefficient. And if we generate a fast graph, if we want a single specialized graph with one certain type and shape information, the specialized graph can be incorrect for dynamic input types, and the program does not include any information about the exact type of every expressions. Finally, the program includes impure functions, which requires the interaction with the global environment outside of the function scope. For example, we store the final state after processing the first sentence, and then retrieve the previous states before processing the next sentence. For such expressions with side effects, we cannot think of any graph operation that correctly accesses the global state of the Python program, because the interaction with the Python heap must happen at program runtime. To summarize, given dynamic features of Python, it is challenging to achieve correctness and the performance of the graph execution at the same time. Because as we have seen before, if we generate the correct graph that exactly follows the dynamic behavior of Python, executing that graph would be very slow. And if we generate a fast version of the graph, the dynamic semantics of Python is not preserved in the converted graph. Now, I'd like to show you how JANUS solves this problem. To achieve correctness and performance at the same time, we use speculative graph generation and execution approach. Even though it is impossible to statically determine the program characteristics, we can make reasonable assumptions about program behavior based on the execution history. JANUS first profiles the program execution a few times and speculatively generates a specialized graph based on the profile information. When training deep learning models, it is common to run a particular code block multiple times to apply the iterative gradient descent optimization algorithm. Therefore, running the specialized graph is likely to be valid for such repeated executions. However, due to the dynamic nature of Python, sometimes it is unavoidable that some of our assumptions become outdated, so we must validate our assumptions. JANUS checks every assumption, and if an assumption is broken, JANUS falls back to the imperative executor and generates another graph based on updated context information. In fact, such a speculative technique has been successfully used by many just-in-time compilers of dynamic languages with managed runtimes like Java or JavaScript. Let me show you the overall workflow on JANUS with an imperative program with a for loop statement. Once JANUS receives the input program, the program is first executed imperatively, while the profiler gathers runtime information for making reasonable assumptions. We modified the Python interpreter for transparent profiling to avoid intrusive source code instrumentation. After collecting a sufficient amount of information, the graph generator tries to convert the program into a symbolic graph. Not only the graph generator executes the standard compiler passes, it also exploits runtime profile information to optimize the graph based on the reasonable assumptions. In this case, the for loop is unrolled 3 times based on the assumptions that the length of a given sequence will be always 3. And to validate this assumption, we add additional operations to check that the length of a given sequence is actually 3, and to abort the graph execution when the assumption is broken. The generated graph gets stored in the graph cache. Then, on following invocations of the same program, the cached graph is executed. This is the fast path that covers most of the program execution. Now, in the unfortunate case where an assumption is wrong, JANUS detects it correctly. And then the system aborts the graph execution and falls back to the imperative execution from the start of the program. After we fall back to the imperative executor, JANUS starts the procedure from profiling again to generate another graph with updated context information. In the case of our for loop example, now a graph with control flow operations is generated, ensuring the correctness of the program. So, this was how JANUS executes an imperative program efficiently while preserving the correctness. Other dynamic features of Python can be handled in the same speculative manner. Before showing the evaluation results, I'd like to briefly explain a few more system aspects that make our system more solid. One extra path that I did not mention is the fallback path from the graph generator to the imperative executor. It ensures the full Python coverage, even though our graph generator does not convert every feature of Python for design or implementation issues. Please see our paper for a more thorough discussion about Python coverage of JANUS. One more thing I'd like to say is that JANUS adds custom graph operations to mimic the behavior of imperative programs that modifies the Python global states. However, as it would be unsafe to fall back to the imperative executor after the symbolic graph updates the Python global states, we have an additional mechanism for ensuring that no global state has been modified at the time we abort the graph execution while in the middle of the program. JANUS writes to the local copy of the Python heap instead of updating the original Python heap. Then, after validating all of the assumptions, JANUS finally writes back to the contents to the original Python heap. Our paper includes more details about how we manage this local copy. Now, I will show you the evaluation results. I'd like to prove that JANUS makes variable models to converge correctly and also performs much faster than the imperative framework, comparable to the symbolic graph framework. Then I'll show you the performance improvements, where the performance improvements come from. We compared JANUS to symbolic and imperative deep learning frameworks. JANUS is implemented on top of TensorFlow and CPython interpreter, using modified TensorFlow and TensorFlow Eager as the symbolic and imperative executors. Current JANUS is written with 4,700 lines of code, along with almost 2,000 lines of code changed on TensorFlow and CPython interpreter. We selected TensorFlow-based symbolic and imperative frameworks to avoid any implementation-dependent performance differences. We used 6 machines connected with InfiniBand network, and each machine had 6 GPUs. We evaluated 11 deep learning models in 5 major neural network categories that I previously mentioned. The programs extensively use various dynamic characteristics of Python. Let's first take a look at the convergence graph. This graph illustrates the ImageNet test error with a ResNet 50 model on 36 GPUs. The x-axis represents the training time, and the y-axis represents the test error, meaning that the throughput is higher if the line is on the left side. The blue line is for symbolic graph execution, and the yellow line is for imperative execution. As you can see, the symbolic graph execution can make the model converge faster than the imperative execution. Now, the red line is for JANUS. As you can see, JANUS can make the model converge correctly, yet much faster than the imperative execution, without modifying the original imperative program. The performance was similar to the symbolic graph framework. For this experiment, the speedup mainly comes from running multiple graph operations simultaneously. To be more specific, the operations for communication and computation could run at the same time, so we could hide the overhead of communication between multiple machines. With imperative execution model, it is much harder to hide the communication overhead in this way, as the communication also runs imperatively. Next, this is the convergence trends of models in other 4 categories, using different numbers of GPUs according to the size of the models. For all models, the symbolic graph execution is much faster than the imperative execution, and JANUS performs well also for these models. Here, each model has a different amount of speedup. Next, I will show you more experiments that analyze the speedup with all 11 models. This is the normalized training throughput of 3 frameworks with all 11 models. We used a single machine here to remove the effects of various communication overhead according to the different number of machines. The x-axis represents a normalized throughput over imperative execution. JANUS, in red colored bars, achieves up to 47.6 times speedup compared to imperative execution with yellow colored bars. And the throughput of JANUS is more than 96% of the throughput of symbolic graph execution with blue colored bars. One thing you might have noticed here is that the performance difference between symbolic and imperative is smaller on a single GPU when training large CNN models. This is because for large CNN models, the hand-optimized operation kernels for NVIDIA GPU dominates the execution time even on imperative executor. We hope that applying further graph optimizations can achieve more higher throughput both for JANUS and symbolic deep learning frameworks. Now, let's focus on the performance of JANUS. As shown in the red colored bars in the graph, simply converting imperative programs to symbolic graphs without specializing the graph improved the throughput by up to 5 times. However, it could not reach the throughput of symbolic graph execution. Exploiting runtime profile information to specialize the graph additionally improved the throughput, achieving comparable performance to the symbolic graph execution. This is the breakdown of speedup achieved by each specialization. For a small CNN model, type specialization achieved up to 18% speedup. Next, for a small RNN model, unrolling the loop achieved more than 2 times of speedup performance improvements. For tree NN models, parallel execution of independent tree nodes achieved up to 10 times speedup. Parallel execution was possible by speculatively omitting the execution orders between multiple Python expressions. Finally, the DRL and GAN models we used were composed of multiple convolutional neural networks, so the performance characteristics were similar to CNNs. Before concluding this talk, I'd like to compare JANUS to other systems and concurrent works. Recently, there have been approaches that try to convert imperative programs to symbolic graphs. In fact, combining the advantages of imperative and symbolic deep learning frameworks is one of the key features that the state-of-the-art deep learning frameworks, such as Google's TensorFlow or Facebook's PyTorch, are trying to add their latest or upcoming major releases. However, as all of them are just one-shot converters without speculative graph generation and execution, they cannot achieve the correctness and performance at the same time. Now, let me conclude my presentation. JANUS combined the programmability of imperative deep learning frameworks and the performance of symbolic deep learning frameworks. It was possible with speculative graph generation and execution with runtime profiling. JANUS succeeded to improve the throughput up to 47.6 times compared to imperative deep learning framework, within only up to 4% difference compared to symbolic deep learning frameworks. It also preserved the correctness at the same time. Thank you very much, and please feel free to ask any questions.
Yes. Hi, once up from Sonos. So as a guy actually worked on compiler for a long time ago, it was a very interesting talk. Thank you very much. It seems like you are chasing the holy grail of the compiler community that compiler community always look for, which is automatic parallelizing compiler. So in terms of that, like from your example, so you have this loop that with the function calls, and then is your verification can catch that function call as a side effects?
Well, in fact, we always inline the function calls. So in fact, function calls is not that special in terms of catching the side effects.
Okay, good. So second short question is, so since you're actually the transform the program, so go back to your original motivation that it's easier to debugging with the imperative program. Is that statement actually still maintains as true, or, you know, I just want to hear your opinion.
Yeah, in terms of debuggability, yeah, we first profiled the program execution a few times, and in that, while profiling, the program is executed in imperative manner, so the developer can still debug the program. And if an exception occurs while the profiling, then in fact the execution falls back to the imperative executor again. So the developer can catch the exception in the imperative executor.
Okay, sounds good. Thank you.
But I have a quick question. So in those plots, when you showed RNNs, then you actually, it seemed JANUS performs even better than symbolic execution. Like, what's the reason? If you go back to the slide with 4 plots at top left, keep going back. Yeah, here. I mean, it seemed, I mean, JANUS is even better than the symbolic execution in the top left plot for RNN.
Yes.
Why?
The performance difference can depend on many factors, and we think this is in the error range. Yeah, but it is true that JANUS can outperform sometimes the symbolic graph execution, because actually the graph generated by automatically generated graph and the graph manually generated looks a little bit different, and sometimes the performance of automatically generated graph is much better, or sometimes the manual graph is better.
Okay, and one last short one. In general, for RNN and TreeNN, like the amount of improvement seems much larger. Like, do they have any specific characteristic that makes it sort of easier to get a lot of improvements over sort of the imperative style?
Yes, as I said before, the GAN and DRL models, they often use the CNN as its components, so they have similar characteristics that for CNN, the operation kernels are usually optimized for NVIDIA GPUs, so the GPU is already saturated on imperative executor, so the performance improvement is smaller than the RNN or TreeNN models. And in RNN or TreeNN models, the size of each operation is smaller, and we have more room to optimize the graph execution.
Hi, Abdullah from Tufts University. So when designing the symbolic representation, it seemed that the correctness heavily relies on capturing all the assertions. I'm just wondering if there's like, does your framework provide formal guarantees that all the appropriate assertions would be captured? Because if they're not, then in a dynamic setting, you know, the program would be running incorrectly, right?
Yeah, in fact, we don't have we don't have any formal verification, but in general, we believe that dynamic just-in-time compilers of dynamic languages also are already working well without formal verification, and we believe that just simple engineering efforts can make the program correctly.
Okay, let's thank the speaker again.
Yeah, thank you.